Hi, welcome to the Semantics lecture introducing composition. Composition will be one of the key building blocks of semantic analysis and the semantic enterprise, along with truth conditions. And it's going to be run along very restricted lines, as it turns out. We've already seen that the syntax will feed the semantics, and that will determine the kinds of structures that we compose. And we'll see that the way that they compose is limited to a handful of recurring rules that can be used relatively freely, depending on what needs to be done for the composition to work. But we saw that the syntax feeds the semantics, so when we take the meaning of a sentence, like Alyssa smokes, that we're actually taking the meaning of the syntactic structure. We can see that in 1. And we see that in 1, right? It's just referring to the handout that goes with this. Now there are 2 lexical items that feed this structure. Right? The first is the noun, Alyssa, and the second is the verb, smokes. And we'll set aside issues of tense, inflection, and so forth. Right now we just worry about just treat it as a single verb. Now the denotation of Alyssa is pretty straightforward. Right? It's the person Alyssa. So what we need then in our semantic structure, the meaning of Alyssa, and that's going to be Alyssa. But the meaning of smokes is a little more complicated because it's not saturated. Alyssa is saturated, smokes is not. And so we can ask, what kind of formal objects these unsaturated expressions correspond to? Now, if you answered functions, that is right, which suggests that the word smokes denotes a function. Well, what kind of words have we seen denote functions? Essentially, we've seen properties do that. Right? We've seen with vowels, for instance. The word val describes a property of objects, and it refers and it denotes the characteristic function that will take anything and give you the set of vowels. Well, we can do the same with a verb. We can define a verb by the set of objects that do the action or enjoy the state that it describes. So let's take, for instance, smokes. If we assume a domain, and we can call that domain D, we can make that domain whatever we want. In this case, let's let D be the set containing Alyssa, President Obama, me, Simon Cowell, and Oprah. Now, in that case, smokes is going to map from that set to the set containing 1 and 0, such that for all x in the domain, D, f of x equals 1 if and only if x smokes. It's just like a val. So we can write that out in our function notation with the mappings as in 5. So Alyssa maps to 1, President Obama maps to 1, I map to 0, Simon Cowell maps to 1, and Oprah maps to 0. And that gets us our function. So we can write it as the function here in 5, as the mappings in 6, or as an abstracted set here in 7. So we have these meanings then. We can say that smokes is this function, and Alyssa is just the meaning of Alyssa is just Alyssa. So how do we get to there though from here? Well, we can do this with a simple rule of lexical insertion, essentially, and this rule is called terminal nodes. We can call it rule number 1. It's the first on the list. And terminal nodes is pretty straightforward. It's defined as follows: if alpha is a terminal node at LF, then the denotation of alpha is specified in the lexicon. That is to say, if you have a node with a syntactic head, then it can be interpreted. What this means, though, is that every syntactic head will need a meaning in the semantics. Or to put it another way, there's no syntactic head that has no meaning whatsoever at LF. And when I say there's no syntactic head, we say a syntactic head at LF. So if there's a syntactic head that has no meaning, then it should be invisible at LF. And that's going to lead to some of the distinctions between PF and LF. Now, as far as that goes, though, we're just going to deal with heads that do have meanings, like Alyssa and Smokes. And so Alyssa means the person, and Smokes means this function, or this set of smokers, essentially. So now how do we compose them? We've inserted these based on a rule called terminal nodes, and we can say, and what we'll do is annotate the head in that way. So we'll say, via the terminal nodes rule, we have inserted the meaning Alyssa. Via the terminal nodes rule, we've inserted Smokes. So we have this structure, right? And we can combine these, and we'll compose them from the bottom up, because the semantics always builds from the bottom up. And nowadays we'd say that the syntax does as well, but that, of course, that depends on your theory. But the semantics only works if you build it from the bottom up. So we start with terminal nodes, and we have the noun and the verb. So in the semantics, though, we don't really have nouns and verbs. Those categories don't do anything in the semantics. We'll keep using them because they're convenient for us to see what's going on, but just remember that these categories don't really mean anything. Okay. So if we combine the noun and the verb, we should be able to get some meaning, right? If Smokes is a function, and it maps whatever you plug in to 1 or 0, depending on whether it smokes, well, you plug in Alyssa, and you'll get 1 or 0. So we can just take this as a function, and then we write it as the argument. Now, why do we do this? Well, that's because Smokes is a function. You can think of it as the f, and we write the argument of the function in parentheses. So the argument is Alyssa. Now, pretty straightforward, right? We combine the noun and the verb, and voila. Right? But this is actually wrong. And the reason why this is wrong is because the noun and the verb can't compose. Why not? Well, there's no semantic reason why not. This is a function, this is an argument. But the reason is in the syntax. Right? If the semantics is reading off the syntax, then what do we have in the syntax? Well, we have the verb is the daughter of the VP. It's not the sister of the noun. The noun is not the sister of the verb, it's the daughter of the NP. So we need to have an intermediate node. The NP has a meaning, the VP has a meaning. And we can lay out an axiom, essentially, of called the syntax-semantics correspondence, by which a node that has at least one daughter is interpreted as the output of the composition of its daughters at LF. Say, if it has one daughter, it's interpreted as the composition of its daughters. If it doesn't have any daughters, then it's a terminal node and it gets plugged in anyways. It'll have a meaning. If it does have a daughter, then it's composed from its daughters. So since this has at least one daughter, it will have an interpretation, and its interpretation will be the output of composing all of its daughters. In this case, there's just the one. Right? So if we were combining two things into one, well, it would be a pretty obvious correspondence. The correspondence isn't obvious here because we're not going to change the meaning. V goes straight to VP. Right. So the NP and the VP combine, and so we just have to have a step that gets us there. And we can do that with our second rule. And we can, and the second rule is based on the observation that a non-branching node like this will have the exact same meaning as its daughter. And that comes out of the syntax-semantics correspondence. which right, says that the meaning of the node is built out of the meaning of the daughters. So we have this rule for non-branching nodes. We call it NN non-branching nodes. If alpha is a non-branching node at LF and beta is its daughter, then the meaning of alpha is the meaning of beta. That's pretty straightforward. So now, using this rule, we can just build up a level. And it doesn't add a whole lot. Meaning-wise, it doesn't add anything. But it helps us keep our correspondence with the syntax, which is what we want to do. So the VP has the same denotation as V, the NP is as N. And we see that on the left and the center trees in 8. Now on the right, you see that there is an interesting change. I've replaced the meaning of Alyssa with the metalinguistic expression Alyssa, and I've replaced the meaning of smokes with the actual function, the characteristic function. Why did I do that? Because they're equivalent. And because it's going to be a lot easier to see what's going on once we do that. Remember, when we have equivalent expressions, we can switch them out, however is convenient for us. And so, the meaning of Alyssa is Alyssa. The meaning of smokes is the function from D to the set containing 1 and 0, such that for all x in D, f of x equals 1 if and only if x smokes. Okay. So how do we combine them? We can't use terminal nodes because S is not a terminal node. We can't use non-branching nodes because S branches. So how do we combine the two sisters? Well, this is where the insight from Frege comes in, and he knows that the unsaturated expression is a function, the saturated expression is an argument, and he got his PhD in math. And any mathematician will tell you that you plug an argument into the function. And so that process is called application. Specifically, functional application, and that's the rule number 3. And that's going to be the heart of the composition. And it's defined as follows. That alpha is a branching node whose daughters are beta and gamma. Then beta, and if beta is a function and gamma is in the domain of beta, then the meaning of alpha, the whole, is the result of applying the argument to the function, beta, gamma to beta. So, and we've set it up so that we haven't defined the domain. So this domain, can be different things, and we'll see that it changes. But for now, it's just the domain, whatever domain of individuals that we're using. So how does this work? Well, we plug in, take the function smokes, this is the f again, and then we plug in the meaning of Alyssa, which is just Alyssa. And then that will get us the result 1 if she smokes, and 0 if she doesn't. And that's essentially a truth value. It is true or it is false. And the condition, if x smokes, is essentially the truth conditions. The truth conditions rely on plugging something in. So this sentence is true if she smokes, and it's false if she doesn't. So the fully saturated sentence denotes a truth value, 1 or 0, and that's an interesting an interesting result that works very well, but has caused philosophical issues. Functional application doesn't actually care what syntactic order the function and argument are in. If you noticed carefully, the arguments beta and gamma in rule number 3 were an unordered set. Right? So the semantics isn't going to care if this is the function or this is the function. The syntax will care. Right? So if the verb comes before the subject or something like that, right, that's going to be linearized in a particular way. The semantics doesn't care. If one is a function and the other one can be plugged in, then it gets plugged in. Simple as that. Right? And that's how that works. And we're always going to write the function and the argument like this. Function and then parentheses the argument. And so we can try some more sentences. All right, we'll try this one. Alyssa fell. And this one's going to have the same structure here. We have fell and Alyssa. So, based on the terminal nodes rule, we have Alyssa here. And we'll have fell over here, which will be the function, let's say from D to 1 and 0, such that for all x in D, f of x equals 1 if and only if x fell. So the truth conditions are going to be right here. Plug in x. If x fell, then it's true. Maps to 1. Maps Alyssa to 1. If she fell. If she didn't fall, it will map her to 0. Okay. Now, this is the denotation of the heads. We need to project to the phrase, so we use the non-branching nodes rule. We do that here as well. And I'm just going to write denotation of fell, because I don't want to write all this again. Right? And depending on the exercise, you'll be able to do that too. Remember, these are equivalent. Now we plug these in. Right, now we can combine these. VP, NP, which one takes the other as its argument? Right? Well, this doesn't matter. Only this does. This is a function. This is in the domain of this function. And so we can plug it in. Now, we can write this whole thing, and we put it in square brackets to show that it's a function and it's got a lot of content to it. It's more than one word, essentially. So for all x in D, f of x equals 1 if and only if x fell. Right, that's the function. And then we take Alyssa and we plug it in. And essentially, the result will be 1 if and only if Alyssa fell. So 1 if she did, 0 if she didn't. Which one is it? Well, it depends on what happened, right? So if you describe a situation as Alyssa fell, and she actually did, then the sentence will be true. If she didn't fall, it's false. And now we can generate that for all sorts of expressions. So that's how functional application works. And that's how the beginnings of composition work. We have terminal nodes, non-branching nodes, and functional application. And that's how they work. So with that, we'll be able to do a whole lot of composition. And we'll get a good start on it starting in the next lecturelet. And for the most part, we'll be using just those rules. We won't need a whole lot else. In fact, Frege figured that we would need nothing else. We're going to see that we do. But for the most part, we won't. For the most part, this is it. You master this, and you've mastered most of formal semantics.